Yeah, so welcome everyone, and thanks Youngsoo for accepting the invitation. So he'll be talking today about efficient physics-constrained data-driven physical simulation. Yeah, thank you.
All right, thank you. Thank you so much for the invitation and kind introductions. I'm very grateful to give a talk to the special interest group on machine learning and dynamical systems hosted by Alan Turing Institute. I hope this opportunity will lead to collaboration between Alan Turing Institute and Lawrence Livermore National Lab in the future. All right, today I would like to introduce many exciting the data-driven physical simulation capability we have developed in the past several years here at Lawrence Livermore National Lab. This is exciting field of research right now, as you all know. So I'm sure you will enjoy the talk today. I was fortunate enough to work with the awesome reduced total model teams here at LLNL and both internal and external collaborators. Of course, all the results I'm going to present today were not possible without these awesome people. All right, let's start by arguing about physical simulations. I think this special interest group is especially interested in dynamical systems. So let's talk about the dynamical physical simulations. All right, there is no doubt that the physical simulations are so essential for the advance in science and technology these days. Well then, how did we get this physical simulations capability, which we are heavily relying on today? I would argue that the data played a major role already now and in the past. Just to illustrate, if you look at how we have advanced the orbital model of the solar system in history, it starts with the Copernican model, which correctly postulated that planets orbit sun, not sun orbits Earth, by the telescopic observations of the face of Venus. Then Kepler interpreted the more observational data of planetary motions by Tycho Brahe to develop Kepler's 3 laws of orbital motions. Then Newton further developed laws of mechanics, gravity, and calculus, which is further advanced to differential equations. Then many physics laws were written in terms of differential equations later on, such as Navier-Stokes and Schrödinger's equations and wave equations and many more equations of motions and dynamics, right? And then computer came along, greatly improving the computing powers as well as the numerical methods of solving these differential equations, thanks to Hilbert, Courant, and many other pioneers. And this is how we have now, the physical simulation capability that is advancing science and technologies. For example, you are looking at a beautiful simulation modeled by smooth particle hydrodynamics for shaped charge penetration. The simulation is well matched with the experiment. This kind of simulation can be run routinely for various applications. However, it has limitation though, that is, it can be very expensive. For example, 1/4 simulation of this shaped charge simulation takes 7.4 days. This is unfortunate in multi-query applications such as design optimization and uncertainty quantification. Therefore, we need reduced order models that accurately accelerate these expensive physical simulations. Here again, data plays a key role of building an efficient reduced order model. Many data-driven reduced order model can be built by following the framework called LaSDI, which stands for Latent Space Dynamics Identification. The LaSDI has 4 distinct steps. First, you have to generate the data. For that, let's consider a parameter space denoted as D here. The parameter space can be initial condition, boundary condition, or material properties of your physical simulation, so whatever you set to be parameter. Then you collect data by solving the full order model with potentially high performance computing machines for several sample points in your parameter space. And then the second step is the compression step, where both linear and nonlinear compressions can be applied. The most popular linear compression technique would be singular value decomposition. If you have a multi-dimensional data, then tensor decomposition would be a good candidate. And the most popular nonlinear compression would be autoencoder. These compressions will form a latent space, and data you created will now reside in the reduced latent space that is much smaller dimension than the full space and much simpler as well. However, we do not know the dynamics of the latent space. Therefore, the next step would be to identify the latent space dynamics. Here, we will try to fit these latent space dynamics data into a certain model. The simplest model can be linear dynamical systems, which is characterized by the linear ODEs. The nice thing about this approach is that it has a closed form solution to this linear ODEs because the latent space dimension is small. Basically, if you take the eigen decomposition of this A matrix, system matrix A, and then you can write the analytical solution as an exponential form. However, the unknown latent space dynamical system might not fit well to the linear model, right? So the more generalized approach would be to fit the data into a nonlinear ODE with, for example, higher order polynomials or trigonometric and etc. Then you find the coefficient in front of those nonlinear terms using a Cindy-like the regression techniques. Another approach is to use a underlying physics. This falls into the traditional projection-based reduced order model approach. In this talk, we will go over all these different types of approaches and how they perform for various physical simulations. Now, once the dynamical model for latent space is identified, it is used to predict a new solution for a new parameter value in a fast and accurate manner. For example, we can take a new initial condition and project it into the latent space and solve the reduced system of equations in the latent space with the updated initial condition. Then the reduced solution can be decompressed to reconstruct the corresponding full order model solutions. Not only for one point, but also many other parameter points you have not seen in the training phase. So it's very predictive and can be done in a very fast manner. By the way, depending on how you incorporate the underlying physics, the data-driven method can be either intrusive and non-intrusive. Therefore, they can be categorized by its level of intrusiveness. For example, dynamic mode decomposition, which is denoted as DMD here, uses linear compression technique, SVD, then uses linear dynamics form for identification. It requires only data, so it is non-intrusive method. More general form, that is LaSDI, which I introduced in previous slide, is also non-intrusive method because it again only needs data. On the other hand, if we use the underlying physics model to identify the latent space dynamics, then it becomes a physics constrained method. And also it is intrusive because we will explicitly use the underlying high fidelity physics solver. Here we denote it as a physics constrained ROM here. All right, roughly speaking, more intrusiveness means more accuracy. So the intrusive reduced order models are more accurate than the DMD or LaSDI approach if the same amount of data are used. On the other hand, more intrusiveness means less speed up. So the DMD or LaSDI methods are faster than the intrusive physics ROMs in general. Also, the physics-constrained reduced order models are more robust in extrapolation than the DMD or LaSDI models, which will become handy in multi-query applications such as PDE constraint optimization or uncertainty quantifications. All right, let's start to introduce some non-intrusive approaches first. The first one is dynamic mode decomposition, so-called DMD. let's say the nonlinear dynamical system is described by this nonlinear ODEs, right? It can be viewed as a semi-discretized version of PDE. Now, DMD aims to find the best approximate linear dynamical systems, right, in this form. To do that, it first collects dynamical data U, the temporal, the snapshots, and put that in the matrix U. Then try to find the linear system matrix A, which maps the previous time step solutions to the next time steps. If we denote the U plus as the time step solution from second to the last, and U minus as the first to the second to the last, then by definition of A, this equation needs to be satisfied, right? Okay, in order to find that A, the DMD performs a linear compression on U minus the dynamics data. Then it forms a reduced linear system of matrix, which is denoted as A tilde R here. Then to find out a closed form solution, DMD computes the eigenmode decomposition, where the eigenmodes and eigenvalues are used for the closed form solutions with truncated SVD mode W here. Here I show you some numerical experiments that demonstrate how DMD performs for several problems. They are advection, Euler, and nonlinear Poisson, and the nonlinear elasticity problems. For all the problems considered here, DMD was able to achieve an excellent accuracy, that is relative error less than way below 1%. By the way, these results are reproductive cases, which is not that useful. So we have recently extended the DMD to be parametric using interpolation. For example, we interpolate the tailored SVD mode W for a specific parameter, for a new parameter. Then we interpolate the reduced linear operator A, tilde R as well for new parameter. Then we compute the eigenmodes, eigendecomposition on the interpolated reduced linear operator. Then combine the new eigenmodes with SVD modes to set an updated closed form solutions. So here is a numerical experiment that shows how this parametric DMD performs on nonlinear diffusion problems, where an initial condition is parameterized by its center location and size. As you can see, the training points use different initial conditions. Then the parametric DMD is tested with initial conditions that were not used in the training. The accuracy is measured in terms of relative error, and they are less than 1%, as you can see, which is an excellent performance. By the way, DMD uses linear compression, right? But the LaSDI, the latent space dynamics identification framework I have introduced in the previous slides, allows nonlinear compression as well. The nonlinear compression will be especially helpful if the dynamics are advection-dominated, or its solution snapshots tend to be linearly independent. For example, the radial advection problems and 2D Burgers problems with a high Reynolds numbers are those kinds, as you can see from this movie. Here, we compress these advection-dominated simulations data with both linear and nonlinear compression and compare the reduced latent space dynamics. As you can see, the nonlinear compression gives a simpler dynamics than the linear compression one. Here, we compare the projection errors between linear compression and nonlinear compression. As you can see from the scales here, the nonlinear compression gives a much smaller projection error. So in terms of accuracy, the nonlinear compression is better than the linear compression if the simulation data is, for example, advection-dominated. All right, let's actually apply this nonlinear compression to porous media flow data. Here we use Autoencoder for compressions for the nonlinear compression. Then for the identification and prediction steps in LaSDI, we train either radial basis functions or artificial neural network, right? And indeed, if the data is advection-dominated, the nonlinear compression through the autoencoder outperforms the one with the SVD, which is the linear compression in terms of accuracy. It gives you much less the relative error. All right, now let's move on to the case where the nonlinear ODEs are used in the identification step. That is more general case than the linear dynamics identification model. Here, the theta here can take any form of functions. And for example, it can take a polynomials, trigonometric, and possibly exponentials. Once the library of the functions are set by user, I mean, you determine that, those library of functions, then the coefficient in front of those the functions can be found by solving a least squares regression problem. By the way, it is hard to imagine that one global ODE can accurately capture all the dynamics over whatever the parameter space you have, all right? Sometimes that is possible. If that is the case, then we call it global dynamics identification model, and we call it the global DI. However, as I said before, since that would not be the case in general, we form a local DI that can accurately cover a specific local region of the parameter space. Here we demonstrate two different types of local DIs, one with the 2 points and another with the 4 points. By the way, you can also interpolate the coefficients of local DI, right? Each local DI will have the different coefficients, and if you interpolate those coefficients, you will be able to get the interpolated DI for any points within these regions, right? And if we take that parameterization technique, we call it point-wise the parametric LaSDI. All right, here you may have a questions. The question being how we choose the training points, which is denoted as red X here. That will obviously affect the performance of the LaSDI. In this example, as you can see, the points are chosen uniformly. However, it is also hard to imagine that the uniform sampling would give you an optimal sampling. Therefore, to address this sampling issue, we adopt a greedy sampling procedure where a point with the maximum error or error indicator is sampled in a one-by-one fashion for a given list of local DIs. So for example, let's say we start with a 4 local DI at the corner, 1, 2, 3, 4 here. Then we randomly samples points in the parameter space, right? And denoted as this red and blue dots here. Then find the location where the maximum error indicator occurs, and which is this red dots. And you build a local DI there. Then we now have a 5 local DI denoted as 1, 2, 3, 4, 5 here. And we repeat this process again by randomly samples the parameter space and the computer error indicators there, then find the next maximum, the locations where the maximum error indicator occurs, and add that points in the next greedy steps. And you repeat this process until the desirable accuracy is met. And this way, we can choose training points suboptimally if it is not optimally, and the desirable accuracy can be achieved. We call this framework G-LaSDI, where G stands for greedy. So it's a greedy LaSDI or G-LaSDI, right? All right, here LaSDI with the uniform sampling and the greedy LaSDI are applied to simple 1D Burgers problems. Both of them takes 25 training points. 1, 2, 3, 25, and here the G-LaSDI takes the 25 points in random, non-random, non-uniform way, following the greedy procedure. As you can see, the uniform sampling LaSDI gets the maximum relative error of 4.5% around here, while the greedy LaSDI achieves the maximum relative error of 1.9 around here. Obviously, the greedy LaSDI shows much better performance than the uniform sampling LaSDI, even though they use the same amount of data, right? Here, the LaSDI and with the uniform sampling and the greedy LaSDI are applied to 2D Burgers problems. Both of them takes 36 training points. Again, the greedy LaSDI outperforms the uniform sampling LaSDI in terms of accuracy, where greedy LaSDI achieves the maximum relative error of 4.6, while the uniform sampling, the LaSDI gets maximum relative error of 22%. Again, the GLaSDI outperforms the LaSDI with the uniform sampling. All right, now let's switch a gear a little bit. So far, all the approaches I have introduced were data-driven only. They did not incorporate available physics information such as mass or energy conservation, etc. However, incorporating these available physics information in a data-driven approach is extremely important. One way of doing this is to use projection-based reduced order model technique. Here, I'm going to introduce a very traditional projection-based reduced order model approach. To do that, we will start with the governing equation represented by the ordinary differential equations again. Here, W is your state variable, and F is your nonlinear function, and T is the time variable, and mu is a parameter. And we first approximate the solution as a linear combination of the reduced basis phi, whose dimension is a lot smaller than the full order model dimension big N sub S. Note that we have applied the linear compression here. And later on, it's easy to imagine that the nonlinear compression is possible as well in this context, right? All right, once you get this, the solution representation, you plug this into the governing equations right here, wherever W occurs. By doing so, you will have a overdetermined system where you have more equations than unknowns. So in order to close the overdetermined system, you apply the Galerkin projections, and where you multiply the phi transpose on left and right hand side for this linear compression techniques. Then it will give you a reduced system of ordinary equations. Note that this reduced system can be considered as identified latent space dynamical systems. Only thing is that we have derived these equations from the governing equations, right? So we have used the physics which is embedded in the governing equations, therefore. All right, then you can apply your favorite time integrator to solve this reduced system. For example, I have applied the backward Euler time integrator, and to demonstrate for the demonstration purpose. This gives us the fully discretized reduced nonlinear system of equations you have to solve in every time step. Here is a catch though. So this nonlinear terms, every time the arguments changes, you have to update this F, but F is scales with a full order model size, unfortunately. So, and then you have to multiply that with a phi transpose, which also scales with the full order model size. Therefore, a special technique is needed, so-called hyper-reduction sampling technique, where you sample and evaluate only important subset of the nonlinear terms to improve that efficiency. So the most famous hyper-reduction technique is DEIM, which stands for discrete empirical interpolation method. The DEIM introduces the nonlinear basis phi of F, and then express the nonlinear term F as a linear combination of nonlinear basis vectors. Then it introduces a sampling matrix Z in front of the nonlinear term F, and that will, samples the important the elements of the F. Now the sampling indices of the matrix Z can be obtained through the various algorithms. DIM and QDIM are the popular ones. Then the generalized coordinates for nonlinear term f of hat can be obtained by solving the interpolation problem. Then you plug this expression into the reduced system of equations wherever the nonlinear term shows up. Then you will end up with these crazy looking equations. However, if you look at it closely, most of the terms can be pre-computed. And this nonlinear term, thanks to the sampling matrix C, you don't have to evaluate everything. You only need to evaluate the ones which is sampled by this C. This is basically how you achieve a efficiency in this classical projection-based reduced model. There are many other hyper-reduction types, GNAD, SD-GNADs, and SNS are others. Anyway, all these hyper-reduction variants more or less follows what I have described here for DEIM. All right, this traditional linear subspace reduced model can be used to accurately accelerate various the dynamical systems, achieving a speed up of 10 to 1000 with a relative error less than 1% or 5%, for example. For example, this linear subspace reduced model has been successfully applied to a tough simulation such as Lagrangian hydrodynamics with time windowing approach. Here you are looking at the cases where the reduced order model achieves the speed up of 14.6 to 87.8 with an indistinguishable accuracy level. That is a relative error less than 0.1%, right? Which is really great. And another great thing about this reduced order model is its robustness with extrapolation. Unlike the black box approach or the non-intrusive method, since the reduced order model directly incorporates the governing equation for the underlying physics, even though it is used to predict the solution for the parameter point away from the training data, it can still give a reasonable accuracy. For example, this graph shows the relative errors of the local reduced order model that is trained at a specific point, which is blast energy of 0.25 here for the seed of blast simulation. As the prediction point gets away from that training point, the accuracy deteriorates, as you can see, but not much though. We still observe that a relative error of less than 1% around this region from 0.1 to 0.4, this kind of accuracy cannot be achieved by purely data-driven methods, like purely non-intrusive methods, because they do not incorporate a physics law. This is the power and the advantage of incorporating the physics in your data-driven model. This has a great implication, for example, in gradient-based optimization. Let's say you do not have sensitivity implementation. As you may know, the implementation of the sensitivity can be quite complicated. In this case, you can approximate the gradient using the finite difference. Here, if you do each function evaluation, for example, at some perturbed point using the extrapolation capability of the local reduced order model, you can approximate the gradient via the finite difference very quickly, right? All right, so in spite of all these wonderful results, unfortunately, the linear subspace reduced order models have a great limitation though. That is, it cannot accurately represent a long time advection-dominated solution with a small basis size. Let's look at the 2D burgers problem that you have seen in previous slides. The solution is very advection-dominated, as you can see from the movies. The linear subspace ROM shows fictitious oscillation in front of the shock wave if the reduced space dimension of 5 is used. The resulting in a relative error of around 34%, which is not good enough for many scientific applications. The limitation of the linear subspace reduced order model comes from the fact that the solution is represented by linear combination of a fixed reduced basis. This issue again can be effectively addressed by nonlinear compression. Formally speaking, we can build a nonlinear manifold reduced order model instead of linear subspace reduced order model. To formally explain the nonlinear manifold reduced order model, here is the governing equation you have seen before, where W is your solution variable. We approximate the solution with this time nonlinear manifold, which is represented by the nonlinear function G that maps a small latent space dimension to full order model dimension. The nonlinear map is obtained through the autoencoder training with the solution data from the corresponding full order model simulations. Note that this decoder is mapping the latent space to the full order state. So it is perfect for our nonlinear map function G. So we use the decoder as the nonlinear map function. Then we plug this nonlinear manifold solution representation into the governing equations and obtain the overdetermined system where you have more equations than unknowns. By plugging it, you are using explicitly the physics embedded in the governing equations again. So it is physics constrained method. Here, you must be careful with the nonlinear terms. Again, as I emphasized before, we need to sample and compute only a subset of the nonlinear terms through hyper-reduction. When you do the hyper-reduction, though, the structure of the neural network matters for the efficiency of the nonlinear manifold reduced order model. Let's first look at the neural network with two hidden layers as a decoder. Let's say that the orange disks in the output nodes are the selected ones by the sampling matrix G. You will notice that many hidden nodes are connected, and as you go deeper and deeper in the hidden layers, the number of connected hidden nodes are increasing very fast. This actually degenerates the efficiency of the nonlinear manifold reduced model because, for example, you have to compute the Jacobian of this neural network, and the computation of the Jacobian as the number of connected hidden nodes increases, it's a very slow process, right? On the other hand, if you use a shallow neural network that is one hidden layer, then you can easily see that the last number of hidden nodes are connected to the sampled outputs, which brings us an ultimate efficiency in the nonlinear manifold reduced order model after we extract the subnet of the chosen nodes. Furthermore, if you sparsify the structure, then you will get even better efficiency. This is basically how we achieve the efficiency in the nonlinear manifold reduced model. Here we compare the performance of all the reduced order models that I have introduced in this presentation. Well, not the deep fluid, but that's non-intrusive methods. Let's compare that. As you can see from the movie, the NMROM and the full order model simulations they are almost identical in eyeball norm. All these, the data-driven method uses the latent space dimension of 5. And furthermore, quantitatively, NMROM achieves a less than 1% maximum relative error, and a speed up of 11 is achieved at the same time, while the non-intrusive method, these deep fluids and the LS-ROMs are struggling of getting the good, accurate solutions. All right, another potential way of overcoming the issue caused by the advection-dominated problem is to use the space-time reduced model. I would like to introduce that. The space-time reduced order model tries to reduce not only the spatial degrees of freedom, but also the temporal degrees of freedom. It does that by introducing both space and time reduced bases. They are combined through the canonical product to represent the whole space and time solution space. Then the coefficient corresponding to the space-time basis vectors are the only unknowns, which maximally reduces the total number of unknowns, right? Then the space-time solution representation is plugged into the space-time formulation and form an overdetermined system again. To close the overdetermined system, we take the norm of the space-time residual and then minimize it. We apply the weighting matrix G bar to achieve a efficiency through the hyper-reduction technique. Skipping the details, we have applied the space-time reduced order model to a large-scale particle transport problems, whose problem size is around the 10 billions in space and time domain. Using space-time reduced order models, we were able to reduce the 10 billion degrees of freedom to only 10, and still gets the pretty much the same physics response as shown in the movie. The full order model took 17.4 seconds with 256 cores, which is not bad, but the space-time reduced order model was able to finish the simulation within 0.006 seconds with only one core. That gives us a wall time speed up of 2,700. Quantitatively, the relative error is less than 1% throughout the time history, which was pretty good. All right. the last topic I would like to share is the component-wise reduced model, which is used for the lattice structure design as a lattice structure design, which serves as a lattice structure design algorithm. This is not particularly a method of handling advection-dominated problems, but it is a nice way of overcoming an issue of distributed parameter space, which is very high dimensional. For data-driven methods, having a high-dimensional parameter space is really bad because you need to generate lots of simulation data. And for some cases, you cannot even generate those data in your lifetime if the parameter space dimension is so high, right? Among many applications of component-wise reduced model, microstructure design or metamaterial design are great interest these days because of the advance in 3D printing. There are many microstructures found in nature, for example, oyster shell, bone, honeycomb, and cactus lattice, etc. All these are there because they can achieve the maximum strength with a light weight. So many industries and labs and universities are trying to mimic these attractive features of the metamaterials by looking for an optimal design, right? By the way, to model the lattice structure, the lattice type structure, it would be the most accurate if we use the monolithic finite element method with very high resolution. However, unfortunately, this is computationally very expensive. This hinders a fast forward calculation, which is unfortunate in design optimization context because manifold calculations are needed to explore the parameter space, right? So to accelerate the lattice structure design optimization process with good accuracy, we have developed component-wise reduced model, which was first pioneered by Professor Petra's group at MIT. We have extended it to lattice structure design process. Let me explain the process of the component-wise reduced model in design optimization setting. First of all, we identify the reference components. Here we have identified simple joint and struct component geometry. Then you introduce a finite element discretization for each reference component. Then we build reduced models for each component, that is joint ROM and struct ROM. Within the process of building component ROMs, we introduce a very important concept called the port, which is an interface that talks to environment. For example, it connects with other component ROM. It can be used to impose boundary conditions. And of course, you can add more components through unavailable ports. It can be used to apply external force. And you can even rotate the component and attach to the system and attach many more in this way as you wish to form your desirable system domain. Then, in design optimization, we assign a density variable to each component, which varies from 0 to 1. Usually, we avoid 0 to ensure the well-posedness, so we set our lower bound to be 0.01. A small density variable implies putting no material there. Density variable of 1 means you put the material there. And we automatize this procedure by solving design optimization. For example, to find an optimal lattice structure, like minimizing the compliance of the system with the mass constraints. All right, here is a numerical example for lattice structure design using component-wise reduced model. Here we minimize the compliance, imposing a constraint of mass being at most 40%. The downward pressure force is applied on the top middle port. Dirichlet boundary conditions are imposed at the bottom corners. The full order monolithic finite element solve involves 2.7 million degrees of freedom, while the component-wise reduced model has only about 4,000 degrees of freedom. We apply the optimization solver called the method of moving asymptotes, so-called MMA, which is very popular in solving density-based topology optimization. The movie shows the optimization history from the beginning. Initially, it started with a uniform density variable and evolves into an optimal the design where the blue component implies no material there, and while red component implies a density variable of 1. So you put the material there. So the final optimal shape, it looks like the upside down, the V shapes, which makes sense, right? And now let's look at the speed up and accuracy of the component-wise reduced total model. For this particular numerical examples, the component-wise reduced total model achieves a 660 speed ups with respect to the monolithic finite element method solve. For accuracy, we easily achieve a relative error of less than 1%. And the nice thing about this component-wise reduced total model is that the accuracy can be tuned by adding more bases. We observe that the exponential improvement of accuracy as we increase the basis size slightly, slight increase. All right, the component-wise reduced total model lattice structure design can be applied for the stress constraint problem as well, where the mass is minimized with stress constraints. This is considered to be a harder problem than the minimizing the compliance problems, both in implementation-wise and the numerical, solution process-wise. Here we introduce the 4 different components. Then we define a computational domain whose shape is L bracket, which is a typical stress constraint problem. Then we assemble and fill the computational domain with 4 component reduced total models, and then delete unnecessary components to find out the optimal L bracket lattice structure. Here is the zoomed in the picture of components in the optimal design with very detailed stress contour plots, which you cannot get with other types of lattice structure design methods, such as homogenization or beam-based methods. In that sense, this component-wise reduced model, the approach is kind of very innovative. Finally, we can post-process the design to get rid of all the hanging structures. They are not needed. It's not supporting any loads there, right? So we get this smooth and nice lattice structure. All right, we have also solved the stress constraint problem for 2D, the bridge lattice structure design with component-wise reduced total models. The paper about the stress constraint, the component reduced model is coming soon. So please stay tuned for that. And finally, I would like to introduce these 2 softwares. With that, you can generate any results I have presented in this presentations. It's open source. Also, we have the web page for one of the software called the libROM, which is the library for the reduced total models, where you can find many other different tools which I haven't presented in this talk. And there, the physics constraint reduced models for various physical simulations are also demonstrated, and you can actually download it and play with it. And additionally, several YouTube tutorial videos about reduced total models are available. They are 5 minutes or 6 minutes long, not that long. So please take advantage of it if you want to learn more about the classical projection-based reduced total model. All right, let me conclude the talk with some summary. I hope I have introduced many interesting reduced total model techniques, data-driven and physics-constrained approaches. The examples I have shown you include non-intrusive approaches, the DMD, and more general LaSDI framework with greedy sampling. The linear subspace reduced total models apply to various Lagrangian hydrodynamics, including seed of blast problem. However, the linear subspace reduced total model was not able to achieve a good accuracy for a long time advection-dominated simulations with small reduced space dimension without special treatment such as time windowing approach. Therefore, we introduced the nonlinear manifold reduced total model that finally achieves a speed up with a great accuracy for advection-dominated simulations with small latent space dimension. The space-time reduced total model that achieves a 2,700 speed ups with a relative error less than 1% for particle transport problem was shown as well. And the component reduced total model for lattice structure design that accurately accelerates the optimization process considerably has been also introduced. finally, I have introduced the web page for libROM, where you can find many useful tools to build a data-driven physical simulation models, right? All right, if you find the things that I have presented today useful for your applications, please let me know so that we may build up some collaborations. With that, let me conclude my talk. Thank you so much for your attention, and any questions are welcome. All right.
All right, thank you very much. Thank you. Any questions?
I have a question. Is it verbal question okay?
Yeah.
Yeah. So yeah, verbal questions are better. Yeah, thank you. Yeah.
Okay, good. Yeah, first off, thanks for the talk. It was very interesting and very helpful for several reasons for comparing the different approaches. I was curious, sort of, first off, if you've done any problems related to, say, multi-phase fluid flow with particular I'm going to forget your acronyms, but the physics-informed approach. And also in a more general sense with these types of problems, can you comment on the number of simulations, after you've included the physics in one way or another using your approach, how many simulations do you need, I would call it, for training data to help build reliable solutions or results? Thank you.
So the first question was, have I applied the multi-phase flow? Apply the physics constraint, the machine learning method to multi-phase flow simulations. Not sure what. Well, okay. So here is the Rayleigh-Taylor instability problems, and right now this was very promising. The results was very, very promising. So although I haven't presented it, but we are now applying this physics constraint machine learning approach to the multi-material and multi-physics, like the hydro or the radiation hydro or the simulations in production code called BLAST to develop at Lawrence Livermore National Lab, and also which is very large scale, and there we are also getting the promising the results there. So answering to your questions, we are applying the physics constraint reduced model, the machine learning techniques to those multi-phase, the flow, more complex system simulations, and the results are very promising. So I do think that it'll play a huge role of accurately accelerating those simulations. And answering your second questions, Rick, was how many training data I need to get the accurate the database, to build the accurate database model. Is what am I rephrasing your question well?
I was thinking more of the latter examples where you had the the physics where you're including starting from the equations. Sorry, I'm like I said, I'm forgetting your acronyms.
Well,
but
like
ones,
like the physics constraint.
Yeah, exactly.
Yeah.
Yeah. So the projection-based linear subspace restorer model.
And your question was how many training data I need?
Yeah, because presumably if you start with the simplest approaches like DMD, then you need a large number of training cases, and you had your greedy algorithm for selecting good training point good parameter choices and so on. But then as you include the physics, presumably you need less and less, fewer and fewer
exactly.
forward models. So it wasn't quite clear to me going through it how far you reduce that. To the number of simulations.
Yeah, that also depends on the applications, right? But you're exactly right. If you incorporate the physics in the model, then we can get away with the less number of data. That's the whole point of using the physics into the model, because the physics constraints approach that lets you, have a stronger extrapolation, the capability, as I have demonstrated in this example. So in this example, it's easy to imagine that each local reduced model outside of your trained region, it still has some good, it can still provide good accuracy. For this particular example, 0.1 to 0.4, the relative error of less than 1% was achieved. And you can imagine that if you broaden this parameter space, let's say the interest parameter space is from 0 to like 1, for example, then at most like the 3 local reduced model, 3 data points will be enough to cover those the parameter space to achieve a relative error less than 1%. So yeah, you're absolutely right. And this the slide is kind of tells you why so, because the physics-based the methods gives you a lot better extrapolation capability than the purely data-driven methods like the non-intrusive method like DMD and LaSDI approach.
All right, other questions?
Yeah, I have 2 curiosities. One is, can your methods deal with singularities of different kind? And the other question is, since you mentioned projection, can you use topology or embedding in different spaces to reduce the dimension?
Yeah. Okay. So the first one, let me answer the first question. The singularity used in different contexts with a different meaning, right? So, for example, in this L bracket, the problems, the structure has a singularity problem at the corner, because numerically the stress quantity there is infinite. So in order to address that, in this component-wise reduced model context, we avoid that singularity problems by actually smoothing our the component, the designs intentionally, so that by smoothness we'll get rid of that the kink at the corner, so that it avoids the infinite stress there. But in general, if there's a problem in the singularity in the high fidelity the model, by construction, the reduced model or the data-driven methods is compressing those solution space and project into the subspace or the low-dimensional nonlinear manifold space, right? So those singularity can be avoided if those subspace you are projecting the solution to does not have that the singularity as the solution space. It just get rid of those singularity solution the case by constructions. However, I don't think it's guaranteed to resolve that issue. And your second question was if you ask that again, sorry.
Yeah, if you're using embedding to reduce reduction, the dimension.
Yeah, well, yeah, that's basically the approach we are taking, right? We are reducing the solution, the dynamics into the lower dimensional space, and that will help what? I don't know. Your question was related to that? Your second question?
Yes, in a way, yes. I mean, all these computational methods have a problem with very high reduction. I mean, reduction of the dimension, because otherwise the CPU or the computational effort is, the complexity is increasing, right?
Yeah.
With the dimension. So there are ways around it via embedding to a low-dimensional space, where some of the difficulties, including actually smearing the singularities, the first question, the things are related anyway. Right.
Yeah, so the performance of this data-driven method very highly relying on the compression techniques you are using. If you come up with the reduced space or latent space, which does not, have a good quality, then there is no hope of building a good data-driven surrogate models, because the accuracy of the model you are building is kind of bounded by from below by the projection error caused by that reductions. So the first thing you have to achieve, whatever the approach you are using, whether it is DMD or the non-intrusive or intrusive, you must have the compression applied to the problems with a very, very low projection errors. Otherwise, I mean, you don't have a hope to get accurate the data-driven methods for your dynamical systems.
Okay, thank you.
Mm-hmm.
Yeah, okay, any other questions? I have a question actually about the DMD. Did you try applying kernel DMD, like kernelized versions, and enforcing physics on it, or?
Oh no, not enforce the physics.
No, that means that if instead of using the DMD, did you try kernel DMD?
Well, okay, so instead of the linear forms, you are. Did we try the?
Yeah, exactly. Instead of using this linear form, you would be working in feature space. That you'll be mapping your variables in some RKHS, and this is how you get the kernel DMD.
Yeah, exactly. That was kind of the point I tried to make in this slide, right? I mean, so instead of the linear dynamics, we can use other forms like more complicated ODEs, or we could inform the physics in actually like. And I was arguing that the classical, the physics constraint projection-based reduced model falls into this category. Like you are trying to find the latent space dynamics using the physics, the governing equations. And
I understand, but I was just saying if you try to combine this with kernel methods, where you can even go to the extra level, where you add when you are not working with your ambient variables, but you work with a modified one in the spirit of kernel methods.
I haven't tried that. Yeah, so that those methodology is getting popular these days, right? I mean,
yeah, exactly. Yeah, this is why I asked you whether you tried. Anyway, maybe you can talk about it in different meetings. Yeah.
Right. Yeah, we're people right now. They are talking about applying the integral kernel, some linear kernels, or the Fourier. The filtering or the wavelets, and they are talking about all sorts of different types of kernels, and then apply this TMD.
Yeah, exactly. This is what I'm saying. That this kernel DMD, and I was trying to see if you tried any of these. Yeah.
No.
Okay. All right. Okay. Yeah. Okay then. Yeah. Any other questions, comments? All right. Yeah. Okay. Thank you very much. Thank you again for the nice talk there. And bye everyone. Thanks. Take care. Bye-bye.
Thank you.
Bye. Yes, bye. Bye-bye.